Hello everybody and welcome back to my channel. My name is Dave and today we're going to be discussing complex numbers and complex roots as they pertain to quadratic functions. If you happen to be using the Holt McDougall Explorations in Core Math Algebra 2 textbook, this corresponds to lessons 2.5 and a little bit of 2.9 in that textbook. If you have a different textbook, don't worry about it. You can still watch this video and use some of the concepts that I'm going to be discussing. What will we be talking about today? Well, in this lesson, we will first talk about the imaginary unit I and the complex number system. Then we'll talk about complex numbers as solutions to quadratic equations and when you have to use them. Finally, in order to check our answers, we will talk about adding, subtracting, and multiplying these complex numbers. First, let's review. So hopefully you should know how to solve a quadratic equation by completing the square. So let's take a look at x squared minus 18x plus 16 is equal to 0. Now, the first thing we should notice is that if you had the expression x squared minus 18x plus 81, this would be a perfect square. So how did we get 81? Well, we looked at the second term, negative 18x. And we recalled that we can find the perfect square by dividing the 18 by 2, the coefficient of the second term by 2, and squaring it. So 18 divided by 2 is 9, and 9 squared is 81. Hence, x squared minus 18x plus 81 is the perfect square trinomial that we're looking for. So, in order to keep everything the same, first we will add 81, then subtract 81 from the left-hand side, and we see this done in red. Next, we can rewrite this as x squared minus 18x plus 81 as a perfect square. So this gives us x minus 9 quantity squared minus 65 is equal to 0. Next, we'll move the 65 over to the right-hand side of the equation, and we'll take the square root of both sides. This gives us x minus 9 is equal to plus or minus the square root of 65. So having taken the square root of both sides, the last thing to do is move the 9 over to the right-hand side. And this gives us a final solution of x is equal to 9 plus the square root of 65, or x is equal to 9 minus the square root of 65. So as I've said, hopefully you know how to solve an equation by completing the square when the right-hand side of the equation is positive. So let's move on to new material. We'll be talking about the imaginary unit I. Now let's think about this in terms of extending a set of numbers that's available to us. So if you want to solve the equation x plus 5 equals 3, and if you limit yourself to positive numbers, you can't solve this. So historically, it took a little bit of time for mathematicians to come up with the concept of negative numbers. But eventually they did, and they found that they could solve it by setting x is equal to negative 2. Likewise, if we want to solve the equation x squared plus 1 is equal to 0, we can't solve it with only using real numbers. However, if we extend the set of numbers that are available to us, it is possible. And we'll do this by simply defining the square root of negative 1 to be the imaginary unit I. And we can in fact use this definition to take the square root of any negative number. And we'll see how to do this later on in the lesson. So let's solve this equation x squared plus 1 is equal to 0. So if we do this, we'll find that x is equal to plus the square root of negative 1 or negative square root of negative 1, which has no real solutions. However, if you allowed yourself to define the square root of negative 1 to be I, then it has two complex solutions. So here we have x squared plus 1 is equal to 0. We'll move the 1 over to the right-hand side to get x squared is equal to negative 1. And then we'll take the square root of both sides, which gives us x is equal to positive square root of negative 1, and x is equal to negative square root of negative 1. Finally, we will use the definition that the square root of negative 1 is equal to I. So we have x is equal to positive I or negative I. I said a while ago that we can use the definition of the imaginary unit that I is equal to the square root of negative 1 in order to find the square root of any negative number. How can we do this? Well, we can do this by recalling a very useful property of square roots. In particular, the square root of the quantity AB is equal to the square root of A times the square root of B. In other words, the square root of some product of two numbers is equal to the product of taking each square root individually. For example, if I had the square root of 128, I could write this as the square root of 64 times the square root of 2, because 64 times 2 is equal to 128. However, 64 is a perfect square, so I could write this also as 8 times square root of 2, or 8 root 2. Similarly, if I had the square root of 720, I could write this down as the square root of 144 times the square root of 5, or 12 root 5. This also happens to apply if one of the factors happens to be negative 1. The exact same logic is in play here. So if I have a square root of negative 25, I can write this as the square root of 1 times the square root of 25. Now recall that negative 1, when taking the square root, we get I, and 25 is a perfect square, which just gives us 5. So the answer is 5i. Also, if I have the square root of negative 27, I can write this as the square root of negative 1 times the square root of 27. I can further break down 27 into the square root of 3 times the square root of 9. And this, of course, simplifies to 3i root 3, keeping in mind that the square root of negative 1 is the imaginary unit I, and that the square root of 9 is 3. So here is our first example. We want to solve the equation t squared plus 125 is equal to 0. So the first thing we do is we move the 125 to the right-hand side of the equation to give us t squared is equal to negative 125. Recall that we can take the square root of any negative number now. So we will write this as t is equal to plus or minus square root of positive 125 times the square root of negative 1. It just so happens that 125 is a perfect square, and recalling that the square root of negative 1 is I, we have our final answer of t is equal to positive 15i or negative 15i. So now let's talk a little bit about complex numbers. A complex number is any number that can be written in the form a plus bi, where a and b are real numbers and I is equal to the square root of negative 1 or the imaginary unit. So looking at this diagram on the right, we can see that we have our real numbers consisting of numbers like 1/2, rational numbers, irrational numbers, decimals, and so on. And we also have our imaginary numbers, I, 3i, negative 5i, the square root of negative 7. We then have our complex numbers, which consist of adding a real number to an imaginary number. Now, we cannot add real and imaginary numbers directly. However, we can combine them to create complex numbers. So every complex number has a real part A and an imaginary part B. So real numbers are simply complex numbers where B is equal to 0. In the same way of thinking, imaginary numbers are complex numbers where A is equal to 0 and B is not equal to 0. These imaginary numbers where you don't have a real part are sometimes called pure imaginary numbers. Now, two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So in other words, if you have two complex numbers, their A's have to be equal and their B's also have to be equal. Before moving on, let's talk a little bit about where these complex numbers exist and a way of visualizing them. All real numbers are said to exist on the real number line. This is something that every elementary school student knows. And we have our positive numbers to the right-hand side of the 0 and our negative numbers to the left-hand side of 0. So for example, here you might have something like 4. You might have something like pi a little bit to the left of it. And over on the right-hand side, you have a number like negative 1.5. Complex numbers extend the one-dimensional number line to the two-dimensional complex plane by using a horizontal axis for the real part and the vertical axis for the imaginary part. So here we have our real axis and we have the numbers 4, pi, and negative 1.5. But when we want to use complex numbers, we add a vertical imaginary axis. So on this vertical imaginary axis, somewhere above the real axis, you might have 3i, and somewhere below it, you might have negative 5i. If you want to plot a complex number, it's going to be inside one of these four quadrants and not strictly on one of the axes. So for example, if I wanted to draw the value 1 plus 3i, it might be somewhere over here. For example, 1 unit to the right and 3 units up. Please note that this is not drawn to scale. Let's move on to our second example, which will have not just an imaginary root, but a complex root. So we want to find the zeros of the function x squared plus 10x plus 26. The first thing we'll do is we'll set the function equal to 0. Next, we will rewrite it by moving the 26 to the right-hand side, giving us x squared plus 10x is equal to negative 26. Next, we'll add 25 to both sides. Once again, we can get 25 by taking a look at the second term, which is 10, dividing it by 2, and squaring it. So 10 divided by 2 is 5, and 5 squared is 25. Now we'll factor it and get x plus 5 squared is equal to negative 1. Next, we'll take the square root of both sides. By now, we should know that the square root of negative 1 is I, but since we're taking the square root, it's positive I or negative I. So therefore, this step gives us x plus 5 is equal to positive or negative I. And next, we have to simplify it by bringing over the 5 to the right-hand side of the equation, which gives us a final solution of negative 5 plus I or negative 5 minus I. Let's look at another example. So we'll do the exact same thing by setting this equal to 0. Then we'll rewrite it by moving the 12 over to the right-hand side. Next, we'll add 4 to both sides, once again making a perfect square trinomial on the right-hand side of the equation. Next, we'll factor it, and we'll get the quantity x plus 2 squared is equal to negative 8. And we'll take the square root of both sides. So doing this gives us x plus 2 is equal to positive I times root 8, or negative I times root 8. Next, we'll simplify by moving the 2 to the right-hand side of the equation and pulling out a root 4 from the square root of 8. This gives us our final answer. X is equal to negative 2 plus the square root of 2i root 2, or x is equal to negative 2 minus 2i root 2. Our final example, we'll solve the equation s squared plus 6x plus 13 is equal to 0. So once again, we'll add 9 and subtract 9 on the left-hand side. Then we'll factor this, and we'll get s plus 3 squared plus 4 is equal to 0. We'll move the negative 4 over to the right-hand side of the equation and take the square root, giving us s plus 3 is equal to positive 2i or negative 2i. And finally, move the positive 3 over to the right-hand side of the equation, giving us s is equal to negative 3 plus 2i, or negative 3 minus 2i. Now, you might have noticed something very peculiar about the results for the zeros of quadratic equations with complex roots. I've summarized them in this table below. In summary, when we have complex roots for a quadratic equation, it turns out that the real part will always be the same, and the imaginary part are always opposites of each other. So for example, if one root is negative 5 plus I, the other root will be negative 5 minus I. And if one of the roots is negative 3 plus 2I, the other root will be negative 3 minus 2I. To sum up what we just saw, if the roots are complex, then the solutions are going to be related. They form what's called a complex conjugate pair. The real numbers are equal and their imaginary parts are opposite. The complex conjugate of any number a plus bi is the complex number a minus bi. In other words, you simply swap the sign in the middle. If a quadratic equation with real coefficients has non-real roots, then those roots are complex conjugates. But it's also worth mentioning that the roots will always be either both real or both complex. You will never have a case with one real root and one complex root if the coefficients are real. So the takeaway here is that when given one complex root, you can always find the other simply by finding its conjugate. And once again, we find the conjugate of a complex number simply by changing the sign in the middle. So how do we go about checking our answers if we have a complex answer? We know that when we solve any type of equation, it's a good idea to check our answers. So to do this, we need to understand how to work with complex numbers. The basic idea is to first treat the imaginary unit I as we would any variable. Then, whenever we see I squared, we're going to change that to negative 1 as per the definition of the imaginary unit. We can also multiply a pure imaginary number by a pure real number. So 5i times 2 is 10i. However, we cannot directly add real and imaginary parts, which is why complex numbers are always in the form a plus bi. To add or subtract complex numbers, we simply are going to add like terms. For example, let's compute the values of p plus q and p minus q, where p is equal to 3 plus 7i and q is equal to 5 minus 2i. So for p plus q, we have 3 plus 7i plus quantity 5 minus 2i. The real parts are indicated in blue, and the imaginary terms are indicated in red. So we'll separate them. We'll add 3 plus 5 because those are both real parts, and we'll add 7i minus 2i because those are both the imaginary parts. And if we do this, we get 8 plus 5i. To subtract, we'll do exactly the same thing. So instead of plus 5, we'll have a minus 5 because we have to distribute the negative. And instead of minus 2i, we'll have 2i. So 3 minus 5 is negative 2, and 7i plus 2i is 9i. So p minus q is equal to negative 2 plus 9i. To multiply two complex numbers, we can simply use the FOIL method, first, outer, inner, last, and then multiply as we would any binomial. Then after it's all said and done, we will change any I squared to negative 1. So for example, if I want to compute PQ, where P has the same values as before and so does Q, I will do it like this. So the quantity 3 plus 7i times the quantity 5 minus 2i. If I use FOIL, I have the first, so 3 times 5. The outer terms are 3 times negative 2. The inner terms are 7i times 5. And finally, the last terms are 7i times 2i. So simplifying this, 3 times 5 is 15. 3 times negative 2i is negative 6i. 7i times 5 is 35i. And 7i times 2i is 14i squared. Now we're going to add like terms, and we will also convert the I squared into a negative 1. So this gives us 15 plus 29i minus 14 times negative 1, or 29 plus 29i. So as our final example, we're going to verify our answer from example 2. So we want to verify that negative 5 plus I is indeed a zero of the function f of x is equal to x squared plus 10x plus 26. I find it a little bit easier to compute each term separately and then to add them up. So that's what we're going to do. So negative 5 plus I quantity squared is equal to the quantity negative 5 plus I times the quantity negative 5 plus I. Using FOIL, we get 25 minus 10i plus I squared. And recalling that I squared is negative 1, this gives us that x squared is equal to 24 minus 10i. For the second term, we can simply use the distributive property to compute the value. So 10 times negative 5 is negative 50, and 10 times I is 10i. Now we add everything up by adding like terms, and we can indeed find that the answer is 0. So this concludes the review of complex numbers, using complex numbers as roots, and a little bit of the operations on the complex numbers. If you have any questions, please feel free to write them down below. And if you liked this video and it was helpful to help you study, please give me a thumbs up and subscribe to the channel. Thank you very much, and I'll talk to you later.